All right, so our transformation T is linear. Okay, so what we're going to do next, by the way, I relabeled these just so that this is not confusing. We first wanted to check that our transformation was linear. That really had two parts. I called these 1 and 2, but 1 and 2 really mean something else. So I just relabeled those real quick, so just to be clear about that. So next what we're going to do is we're going to figure out what happens to our basis vectors 1, 0, and 0, 1 in this linear transformation. So just to recopy it, our linear transformation, T of xy is 4x plus 3y, x minus 2y. And so this part is perfectly straightforward. T of 1, 0 is going to be, let's see, if x is 1 and y is 0, we're just going to get 4, 1. And T of 0, 1 is going to be, let's see, if x is 0 and y is 1, we're going to get 3, negative 2. And so we just get 4, 1 and 3, negative 2. Okay. What we're going to talk about in one of the big, I don't want to spoil this, but I also don't want to hide too much of what's going on. So at the risk of a spoiler here, I want to point out that you can rewrite our linear transformation as a matrix multiplication. And so the matrix that we're going to get, the matrix that we're going to get is if I have T of xy, that's going to be 4x plus 3y, comma x minus 2y. That's going to be some matrix times xy. And I want to think about what is that matrix. And it turns out that this matrix is going to have columns that are exactly these values, T of 1, 0 and T of 0, 1. So it turns out that our columns are going to be 4, 1 and 3, negative 2. Okay, so it turns out that's really what our linear transformation is. Okay, T of xy is going to be, this transformation really is you take this matrix A, right? So I'm going to write this T of V is AV, where A is our matrix 4, 3, 1, negative 2. And V was our matrix xy. That's really what our linear transformation was. This is important. Okay, this is a nice way to represent this linear transformation. It turns out that the transformations that you can write as matrix multiplication are exactly the linear transformations. And every linear transformation, so not only is it true that every linear transformation you can write as a matrix, but every matrix multiplication translation like this is also linear. So in a strong sense, the linear transformations, are exactly the ones of this form. So of the form T of V is equal to AV. Okay, so that's exactly the linear transformations that we'll talk about. I need to be a little bit careful here. So this is definitely a true story. I need to be a little bit careful about the thing I'm thinking about is how do we map. So we're allowed with any vector transformation to map any vector space to any other vector space. How does this matrix account for mapping? So what about mapping R2 to say P2? And so I need to be a little bit careful here. But it turns out that what I've said is essentially true with, you just have to kind of clarify how this is the same. So we'll go through and we'll talk about this in detail. But it's not clear how would you go from R2 to P2 just using a matrix. Okay, and so what we need to do is we're going to talk about some related topics such as change of basis, and there's a lot of material here that's going to kind of flesh out this whole picture, but what I've said is morally true, right? Linear transformations are exactly the ones that have a matrix in them, that have a matrix attached. So linear transformations are exactly the transformations of this type, okay, with some interpretation that you may have to do at the end to go from one vector space to another. Okay, but forgetting about that interpretation, what I've said is exactly right. Linear transformations are exactly the ones of this form. Okay. I should point out that these transformations are also all linear. So you can just check, and I'll leave this to you to do on your own. You can pause the video or you can do whatever you need. But you can just check that if you were to take this linear transformation, T of V being AV, so you can check that T satisfies both conditions. So that T satisfies additivity. So that T of U plus T of V is T of U plus V. And homogeneity. Okay, so you can check that it satisfies both of those. So T of C U is C T of U. Okay. So I'll leave that to you to check that those are always linear. And the harder direction is, of course, that everything linear is of that form. All right. What I want to do now, though, is I want to think about part 3. So part 3 was, so if I just scroll up, I want to find the image of the vector 2, 3, and I want to find it in 2 ways. And the first way is just the perfectly straightforward plug-it-in way. I don't have a name for that, but we're just going to take T, we're going to plug in the vector 2, 3. And if we take our vector, remember that I've said a lot, so I just want to rewrite our vector T of xy is the vector, so this is the vector 4x plus 3y, x minus 2y. Okay. And so that means T of 2, 3 is going to be, let's see, 2, 3 is 2, so if x is 2 and y is 3, we're going to get 8 plus 9, and we're going to get 2 minus 6. So it turns out that that vector is going to be, our image rather of 2, 3, is going to be the vector 17, negative 4. That's one way to do it, perfectly straightforward. No other comments there. But what I want to do is something a little bit more interesting, and this will shed a little light on why we care about linear transformations, why they have the properties that they do. What I'm going to do is I'm going to write 2, 3 as a linear combination of the vectors 1, 0, and 0, 1. So if I take 2, 3, and I write it as a linear combination of the vectors 1, 0, and 0, 1, there is exactly one way to do this. I know that there's at least one way to do this because the vectors 1, 0, and 0, 1 span R2. I know that there's a unique way to do this because 1, 0, and 0, 1 are linearly independent, and therefore, because it's a basis, these two vectors both span R2 and are linearly independent vectors of R2. And so that means that for every input vector, there's a unique way to write every input vector is a linear combination of those two vectors, right? Uniqueness shouldn't be too much of a shock here, right? There's no other way to write 2, 3 as a linear combination of those two vectors. But that's where linear independence and span are going to come into this whole picture. Okay, and now, because we've already seen that T is linear, we can apply what we know about T being linear. So first of all, if I have the sum of two inputs, okay, so if I have two inputs being added, and then we're going to plug those into the transformation, that's the transformation of each one. So T of 2 times 1, 0 plus t of 3 times 0, 1. So we've already proven that t is linear. This is the same transformation we've been working with for this last example, even in the last video. So we know it's linear, so that means that it's additive. We can split up the inputs in that way. And it's homogeneous. So homogeneity tells us that we can also bring out these constants. This is going to be 2 times t of 1, 0 plus 3 times t of 0, 1. And hopefully now you can feel why, just intuitively feel why, if you know the images of 1, 0, and 0, 1, then you know everything, right? Because let's just think about what happened. We wrote 2, 3 as a linear combination of our basis vectors. There's a unique way to do that. Because of linearity of the linear transformation, we can rewrite our input in this way. So you can separate it by first by linearity and then by homogeneity. And so if we know these two values, we know everything. Okay, because we could have done this for any input vector, and in fact, we will do this for any input vector in a second. So t of 1, 0, we said was 4, 1, and t of 0, 1, we said was 3, negative 2. And so you can just check that if I were to take 4, 1 and multiply by 2, we would get 8, 2. And if you were to take 3, negative 2 and multiply by 3, you get 9, negative 6. Add them up, you definitely get what we want. We definitely get 17, negative 4, which is what we already knew we should get based on our previous calculation. So we got 17, negative 4. Okay, so what I want to do is just take 1 or 2 more minutes and do that process again in general. So I want you to notice that if I were to just take the input vector, say a, b, and think about what's the output going to be for some generic input a, b. What's going to happen by the same process is you're going to write this is a times 1, 0 plus b times 0, 1, and you're going to write that inside the function t. So in the argument here. You can split it up that way. Because 1, 0, and 0, 1 is a basis, there's a unique way to write every vector AB as a linear combination of those two vectors. And so next, we're going to apply linearity. We're just going to do it all in one step by homogeneity and by additivity. We can write this as A times t of 1, 0 plus B times t of 0, 1. And we know t of 1, 0 is going to be 4, 1. And we know that t of 0, 1, we saw that was 3, negative 2. And so what we end up with is exactly what we would expect if we were to just take, straightforwardly take our x's and replace them with a's and take our y's and replace them with b's. We get that this is going to be 4a plus 3b. And in the second component, a minus 2b. Okay, so this is what I want to think about here. One last way to think about this problem. T of AB, we just said that was 4a, I'm going to leave a little room here, 4a plus 3b, and a minus 2b. Okay, and we also said that was the same as multiplying by our matrix, where the columns were the outputs of our basis vectors, 1, 0, and 0, 1, and then we're multiplying that by a generic vector, AB. Okay, so that's a good perspective just to see how everything is working. This actually gives us a nice perspective on matrix multiplication and why it works the way it does. So let me actually just add in one extra layer here. This is the same as A times 4, 1 plus B times 3, negative 2. Okay, so this ties in a lot. This tells us why matrix multiplication is the way it is. Linear transformations are exactly the things that are represented by matrices. Matrices are linear transformations. There's a lot going on.